Next, collision theory and activation energy. Now, suppose we have a beaker of cold water and a beaker of hot water. When you add sugar cubes in them, the one with hot water will dissolve faster than the one in cold water. To explain the different rates of chemical reactions, Max Strauss and William Lewis came up with the collision theory in the early 1900s. The first postulate of the collision theory is that particles must collide with one another in order for them to react. Most particles will act like the billiard balls in a game of pool, and when they collide, they bounce off each other. The collision is not all that is needed in order for a reaction to occur. The particles must also collide with enough energy to break and form new bonds. The minimum energy required to kickstart a reaction is called the activation energy. Some reactions require very little, and some require more to get started. You can think of a reaction as trying to roll this ball through the green path. If we have enough energy to roll it uphill, it is going to roll down to the other side. In other words, the ball had some energy at the beginning, which is potential energy, and we lost some of that in the end, but the ball did not go there on its own. We had to put in some energy to get the motion started. So this initial energy is the activation energy. In terms of chemical reactions, the reactants are here and products on the other side, and this is an exothermic process. An endothermic process will look like this. If we don't have enough activation energy, the ball is not going to get over the hill. And that is exactly what happens during chemical reactions. This graph shows a hypothetical reaction between atoms A and a molecule containing atoms B and C. The activation energy, EA, is the amount of energy needed to get the reactants to the transition state in which bonds are broken and new bonds are formed. This transition state usually lasts for a fraction of a second. In this reaction, the products are molecules AB and the atom C. Because this is an exothermic reaction, some of the energy stored in the reactants is released. Often, activation energy can be a barrier that prevents chemical reactions from occurring. For example, if methane and oxygen are mixed together in the same container, they collide, but there is no reaction until a flame or a spark is added. To react, the molecules must collide with sufficient energy to break the oxygen-oxygen and carbon-hydrogen bonds so that new bonds can form. This additional energy is the activation energy. An energy diagram can help show these energy changes. Initially, the oxygen and methane molecules collide, but they lack sufficient energy to react. A flame supplies the activation energy that is needed. At this point, bonds break and new bonds form in an exothermic reaction that releases energy. The energy released supplies enough energy for other molecules to react, and the mixture explodes. In the air, nitrogen and oxygen are continuously colliding but lack sufficient energy to react. Heat from lightning supplies the activation energy to break the bonds, and new bonds form in an endothermic reaction that absorbs energy. Generally speaking, most reactions will occur faster when temperature is increased, because temperature is the average kinetic energy of particles. With more kinetic energy, the particles move faster and collide more often with higher amount of energy. Now, for most reactions, there is still one more factor: orientation. Even if particles collide with sufficient speed, if they don't do it in the correct orientation, a reaction won't happen. In this reaction of nitrogen-1 oxide and ozone, the reaction did not occur because the oxygen of each molecule touched during the collision. The collision is said to be unsuccessful. But if the nitrogen touches the oxygen, a reaction occurs, making oxygen and nitrogen 4 oxide. This is a successful collision. So the 3 key ideas of the collision theory are that the particles must collide to react. They must have sufficient energy to break and make bonds, and they must collide in the correct orientation.